Hi, Assalamualaikum. I'm Najiha and we are from Group C. So for this week, we will present our experiment 6, Bourdon tube pressure gauge, which is open-ended experiment. Our group members is Nordina binti Abdurrahman, Anissa Afika binti Ismail, Nurul Isha binti Abdurrahman, and me is Nurul Fatih Najiha binti Sukuto. So I will continue our presentation with summary. The purpose of the experiment is to calibrate a Bourdon tube pressure gauge using dead weight. We are loaded on the piston and the indicated Bourdon tube pressure was read. In this experiment, the error and percentage of error that occur inside the Bourdon tube will be calculated and compared to the actual pressure that exerted by the total mass. According to the experimental result, the error that occurs in the Bourdon tube is inconsistent. Instrument calibration is one of the primary processes used to maintain instrument accuracy. It is the process of configuring an instrument to provide result within an acceptable range. Known weight have been applied on the anti-weight calibrator to apply pressure to a fluid for checking the accuracy of readings from a pressure gauge. Various types of pressure measurement instruments have been used to measure the pressure intensity at any point in static or moving fluid. One of these devices is the Bourdon tube pressure gauge. Bourdon tube pressure gauges are most widely used nowadays because of their reliability, compactness, low cost, and ease of use. It consists of a curved tube of elliptical cross-section bent into a circular arc. When pressure is applied to the tube, it tends to straighten out, and the deflection of the end of the tube is widely used for stream and compressed gases. The pressure indicated is the difference between the system pressure and to the exterior ambient pressure, and is usually referred to as the gauge pressure. So I think that's all from me, and we will continue our presentation with the next presenter. Thank you.
Hi, my name is Nordina and I'll be explaining about the theory, apparatus, and the procedure of this experiment. First, for the theory, for the Bourdon gauge, as in the figure, is fitted with a transparent dial which lets you to see the internal workings of the gauge. The gauge consists of a thin-walled, closed-ended tube which is oval in cross-section. The tube is bent to an angle of 270 degrees along with its long axis. The open of end the tube is welded to hollow mounting block, which allows the pressurized fluid to reach the tube. The pressure from the source is thus directly transferred to the inside of the Bourdon tube, and the oval tube becomes rounder as a result of the applied pressure, since a round cross-section has the maximum area for the given circumference. The Bourdon tube begins to uncurl as it becomes rounder, causing it free and to pass. A system of linkage and levers transmits this motion to the gauge needle, which moves over the scale. And for the second one is dead weight calibrator. Dead weight calibrator is the standard precise is to use a system called a dead weight calibrator to apply known pressure to the gauge. The normal calibration procedure is to load the gauge for known pressures using a dead weight calibrator, including a liquid of non-specific gravity used as water as liquid. This dead weight tester uses a simple piston and cylinder arrangement to provide a source of pressurized liquid. In the experiment, water will produce a better result than oil, which is transmitted to the gauge, since the true pressure of the liquid can be easily calculated. The value can be compared directly to the reading on the gauge over the completed scale range. The scale range is the range of pressures from 0 to full scale deflection value. The dead weight tester consists of a cylindrical piston which is free to move vertically in a close-fitting cylinder. As for the equations, the use of pistons and weights with the cylinder generates a measurable reference pressure. We use the equation which is P is equals to F over area, which is pressure is equals to force applied to the liquid in the calibrator cylinder in N over the cross-sectional area of the piston in meter cube. Also, we use the equation for force equals to mg, which is m equals total mass including the mass of the piston in kg, and also the acceleration due to gravity meter per second cube. As for the apparatus, shows the Bourdon tube pressure gauge, dead weight tester, and also 1 kg piston. Next, for the procedures, the apparatus was set as in figure in the apparatus. The test gauge reading was ensured to be 0 and 1 kg was put to the Bourdon tube pressure gauge. The air bubble inside the tube is removed by rotating the piston softly. Then the first reading of pressure gauge in kilopascal is taken after the system is stabilized. Then the initial weight of 0.5 kg was put on the piston. After the system is stabilized, the second reading of pressure in kilopascal is taken. Then the weight on piston was increased by 0.5 kg mass increment. Every 0.5 kg of weight was added to the piston weight. The reading of pressure gauge in kilopascal is taken. Then step 5 to 6 is repeated until the maximum weight of 5 kg is applied to the gauge. After that, the weight is unloaded from the piston by decrement of 0.5 kg. When every 0.5 kg weight unloaded from the piston, the reading of pressure gauge is taken. Then step 2 to step 7 is repeated for 3 times to get the average reading. Lastly, all the data is recorded in the table given. That's all from me. Thank you.
Assalamualaikum. Now we are entering raw data and analysis part. So as you can see here from the slide, we have a table, and from the table there are at least 11 readings taken. As the first reading, there are no mass added and the total mass even without the weight is 1 kg. Then for second until the 11 reading, mass added by 0.5 kg until 5.0 kg was added, and the total mass until 11 reading is 6 kg. Next, we also record actual pressure and the gauge pressure. For the actual pressure, which is pressure exerted by total mass, we can see that the pressure increases as the total mass increases, starting by 30.9 kilopascal for a mass of 1 kg and ending with 185.5 kilopascal for mass of 6 kg. Gauge pressure also the same, which pressure increases as the total mass increases. But there are 2 categories for gauge pressure, which are loading and unloading. For each category, we took at least 3 readings of pressure for each mass. However, for total mass of 5 kg, 5.5 kg and 6 kg, the loading pressure are constant. The unloading pressure are constant. After taking 3 readings of gauge pressure for each mass, average gauge pressure are calculated. We then calculate the percentage error for loading category. The highest percentage is 35.3% with the total mass of 1 kg, which is mass without any added mass, and the lowest percentage for loading category is 13.1% with total mass of 5.5 kg. As for unloading category, the highest percentage is also 35.3% with the total mass of 1 kg also, and the lowest percentage, which is 0.6% with total mass of 4.5 kg. That's all for raw data and analysis. Thank you.
Hi, Assalamualaikum everyone. Thanks to Isha, I'll continue with the results. Okay, the experiment data table with percentage error is shown in table 6.1. Okay, start from the left side. We have mass for mass added and total mass in kilogram, and followed by actual pressure, which is pressure exerted by total mass in kPa, and then followed by gauge pressure in kPa, which for loading and unloading. For this experiment, we have repeated for 3 times and we calculate the average for gauge pressure, and the last one is percentage error in percent for loading and unloading. Constant data for this experiment is plunger cross-sectional area, which is 317.31 mm squared, and piston plunger total mass, which is 1 kg. Okay, next, the discussion for the first discussion is percentage of relative error for the theoretical and measured pressure gauge, which is experimental. Okay, based on table 6.1, the theoretical pressures in the system were calculated and the results were compared to the measured, which is experimental pressure gauge. The percentage of relative error between the calculation and the experimental results can be determined using the equations, which is pressure theoretical equal to F over A, and F is equal to M multiplied by G. In order to calculate the pressure in the table 6.1, the definition of pressure is used. The formula is shown where P theoretical is theoretical pressure, F is force in Newton, M in mass in kilogram, A is cross-sectional area of the plunger in square meters, and G is gravitational acceleration in meters per second squared. The resulting unit of this calculation is 1 kN per square meter or 1 kilopascal. The relative error for the theoretical and measured experimental pressure gauge can be calculated by subtracting the measured pressure gauge and the theoretical result, then divides the value with the theoretical result. For the percentage error, it can be evaluated by multiplying the relative error that has been calculated before in modulus with 100%. The data for the results are shown in table 6.1. The second discussion is source of error and method to minimize the error. Firstly, parallax error is occurred where the observer's eyes are not perpendicular to the scale of the Bourdon gauge during the value of gauge pressure is observed. How to minimize this error? We have to make sure the eyes are perpendicular to the scale of the Bourdon gauge when reading the scale. Second, hysteresis error, which are errors that almost always caused by mechanical friction on some moving element, such as Bourdon tubes. Okay, to reduce friction and the air bubbles inside the cylinder tube, rotate the piston and the accurate pressure reading can be obtained. Next, the sensitivity of the apparatus towards shocks and vibrations, such as the reading will defect when the table where the apparatus located are accidentally being moved. Okay, how to minimize this error? We have to ensure that the surrounding where the experiment was performed is in a good and suitable condition, so that all members can perform the experiment comfortably and repeat the experiment for at least 3 times to get an accurate value. Lastly, the big deviation of the scale reading of the dead weight pressure gauge calibrator is one of the error. How to minimize this error? To get an accurate value of the result, the scale reading should be more sensitive. The next discussion is repeatability and accuracy of this experiment. Repeatability of Bourdon tube pressure gauges mean essentially the same thing. It means within the realm of flow meters or other measurement devices. It is a measure of how consistently the gauge is inaccurately repeating the same measurement if all conditions remain the same. Next, accuracy is similar as repeatability, which equally and independently important in determining the quality of Bourdon tube pressure gauge. It can measure how effectively a pressure gauge in repeating upscale reading on the downscale if all conditions remain the same. That's all from me. Thank you. We move to the next presenter.
Okay, so for the last one is conclusion. Upon considering the varied degree of error during this experiment, this particular attempt is not a reliable method of calibrating the Bourdon pressure gauge. To ensure proper calibration, measurement tools must have a reliable system setup that does not introduce sources of error to the device. The pressure gauge could not be accurately calibrated with the apparatus used in this experiment due to several sources of error. These sources include, but are not limited to, leakage, pure lubrication, trapped air, mechanical fatigue, pure weight calibration, differential dead weight, messes, and general user error. Upon repeating this experiment, a truly sealed piston cylinder device should be used along with a uniform set of dead weight. In addition to this, a high lubricity fluid should be used instead of water to prevent any restricted motion. With this adjustment, the experiment may be repeated and re-evaluated as a reliable calibration method. So I think that's all from me and us. Thank you.